Assalamualaikum and dear students, this is an EC672 Flight Dynamics and Control lecture series on week 7 during our MCO time. As you know my name, so this is the presentation for our new chapter. So previously we refer directly from the textbook. Now this time I turn it into a slide, two slides, but the content is still very much the same. So what we are covering in chapter 4, there are 9 items beginning with historical perspective and second order differential equations, and then we proceed to pure pitching motion, stick fixed longitudinal motion, longitudinal approximation, and the influences of stability, derivatives of the longitudinal modes of motions, the flight qualities, flight simulation, and summary. Now bear in mind that this chapter is all about longitudinal motion. So we are going to focus on the longitudinal motion only. Okay? There will be another chapter, which is the next chapter, will focus on the lateral and directional motion. But the order of the content is very much the same. Now, historically, in 1897, Frederick Lancaster was studying motion of gliders. He conducted experiments with hand-launched gliders and found that these gliders would fly along a straight path if they were launched at what he called the glider's natural speed. And launching the glider at higher or lower speed would result in an oscillatory motion. Later on, this is called Foucault. Now, he's not the only one who actually discovered this. Uh, about 900 years before that, or maybe 800 years before that, Abbas ibn Firnas, a Muslim scholar from Spain, also discovered the same thing. Okay, now we also notice that if launched at its natural speed and then disturbed from its flight path, the glider will start oscillating along its flight trajectory. So there are two ways that it will start oscillatory motion. One, if it's gliding at higher or lower speed, meaning that other than its natural speed. And then secondly, if there is disturbance, for example, there is wind gusts or somebody is moving the control surface, then it will start oscillating. Lancaster called the oscillatory motion the Foucault motion. So he wanted to use the Greek word meaning to fly to describe his newly discovered motion. And actually, Foucault means to flee. Whatever. Okay. Apa-apalah, tak kisahlah kan. But most importantly, you understand that the first, more or less the first lah, okay, flight dynamics, motions, the discover is actually the Foucault motion. Okay. But actually Foucault maksud dia lain. Okay. So kenapa dia ni jadi? Sebab ada balance antara kinetic energy and potential energy. So when you have excessive speed, you tend to climb. Okay. So you dah belajar dalam subjek yang lepas, NEC 671. When you have excessive speed, your speed is higher than your drag. For example, you have additional lift. So you climb up. As you climb up, your speed will be reduced because your altitude is getting higher, your speed will be reduced, and you are also gaining potential energy. So as you gain the potential energy, you lose kinetic energy. Then you start to descend. When you start to descend, you gain kinetic energy, but you lose potential energy, and it will happen oscillate lah, naik turun. Okay, and then the math part of it, of flight vehicle motion was first developed by G.H. Bayer and he was aware of Lancaster's experimental observation and set out to develop math equation for dynamic stability analysis. And it was published in 1911, so a long time ago, um, probably what the first 10 years after the Wright brothers started to fly. He made significant contributions in the analysis of vehicle flight motion, and he laid the math foundation for airplane dynamic stability analysis developed from the concept of aerodynamic stability derivative, and recognized that the equation of motion could be separated into a symmetric longitudinal motion and an unsymmetric lateral motion. Experimental studies were initiated by Bairstow and V.M. Jones of the National Physical Lab in England and Jerome Hunsaker of MIT to determine estimates of aerodynamic stability derivative used in Bryan's theory. So in addition to determining stability derivative from internal tests of scale model, Bairstow and Jones non-dimensionalized the equation of motion and showed that with certain assumption there were two independent solutions, that is one longitudinal and one lateral. Okay, so that is basically all about the historical perspective. Oh no, not really. Ada extension lagi. In the late 1930s, NACA, or National Advisory Committee of Aeronautics, conducted an extensive flight test program. So many airplanes were tested with the goal of quantitatively relating the measured dynamic characteristic of the airplane with the pilot's opinion of its handling characteristic. These experiments laid the foundation for modern flying qualities research, and in 1943, in the middle of World War II, Gilruth reported the results of the NACA research program in the form of flying quality specification. So for the first time, the designer had a list of specifications that could be used in designing the airplane. If the design complied with the spec, one could be reasonably sure that the airplane would have a good flying quality. So that is what we are covering now. Basically, we have studied the derivative, the coefficient derivative, and everything. Now we want to look at the motion, okay, and specifically the longitudinal motion. Okay, let me stop here first before I continue to the second part.